Let's start, but before Grigorii starts, let me recall to everybody that you may and are expected to apply for a summer school, which will take place in Sochi in the beginning of August. If you enter the website of International Laboratory of Cluster Geometry, then you will find a reference to application form. The application can be valid till May 15.
Это объявление означает, что школа будет проходить по-английски?
Нет. Значит, до 15 мая можно подать заявку на участие в летней школе лаборатории кластерной геометрии. Вот. На сайте лаборатории имеется ссылка на регистрационную форму.
В начале первой недели августа в Сириусе.
Да. Okay, now you will start.
Okay, let me recall what we are talking about. So we have some graph G. We assume that this graph is non-oriented. And today we will consider such examples that there will be no multiple edges in this graph. But in general, this story works when G is allowed to have multiple edges, and 1 week ago it had multiple edges. So G may have edges, but not today.
And loops change nothing, and therefore they are not allowed. Yeah.
Yes, we may assume that loops are not allowed. We may assume that they are allowed, but indeed they change nothing. And we consider Laplacian matrix. Which is defined, it is denoted by Q of G. It is defined as a difference of such two matrices. Here we have two guys. A of G is the adjacency matrix, or it has so its elements. So both of these all these matrices are they are square. Their rows and columns are labeled by vertices of the graph, and it's the elements of A of G are just the number of edges between the corresponding vertices.
Yeah, and in this case, we do not choose some orientation. Yeah, we still have a symmetric matrix rather than skew-symmetric one.
Yeah, so AG is a symmetric matrix. And D of G is just a diagonal matrix, and on the diagonal we have degrees of the vertices. So the difference with these two matrices is also a symmetric matrix, and its rows and columns sum up to 0. So we are interested in eigenvalues of the Laplacian matrix. So here lambda 1 is the smallest one, lambda n is the greatest one. We know that they all are real non-negative numbers, and the smallest number is just 0. So we know. So since sum of elements in rows are zeros, then we have eigenvalue 0 and the corresponding eigenvector is just the vector of ones.
I always think about eigenvectors as columns rather than rows.
Okay, yes, it makes sense. And also let us know, I recall that the multiplicity of the values of the zero value is just the number of connected components in the graph. So in other words, so when we have that lambda 2 is equal to 0 if and only if the graph is not connected. Okay, so we know all this, and now we are going to formulate some results about some classical invariants of graphs in terms of these eigenvalues. And we shall start with the the first invariant I want to consider is the connectivity of graph. Namely, we have two types of connectivity. We have edge connectivity and vertex connectivity. Let me define these two notions. So firstly, G is called KH connective.
Connected.
Connected, yes. If it remains connected when we remove less than k edges. So for any edges, A1, A2, AI, I is less or equal to k minus 1, this graph is connected.
Значит, если мы при стирании в графе любого количества ребер меньшего k получаем заведомо связанный граф, то граф называется k-связанным, k-реберно связанным или реберно k-связанным. В частности, в реберно k-связанном графе не может быть вершин валентности меньше, чем k. Если валентность вершины меньше, чем k, то мы можем удалить все ребра, которые из нее выходят, и изолировать ее.
Yes.
Нет?
Yes.
Yes. I see.
So the related notion of edge connectivity, it is denoted as eta of G. It is just the greatest number k, the greatest k such that G is KH connected. So in other words, the edge connectivity is the least number of edges that one should remove from the graph in order to make it not connected. For example, if we have if the graph G is connected, then we can say that his edge connectivity is greater or equal than 1. Moreover, if G has no bridges, then its edge connectivity is greater or equal than 2.
Значит, мост — это как раз вещь, которая, это ребро, удаление которого увеличивает число компонент связанности в графе. Если граф был связан, то в нем становится 2 компонента связанности. Но поэтому понятно, что если нет мостов, то связанность, реберная связанность не меньше 2.
Okay, this was about edge connectivity, and now about vertex connectivity. So G is called K vertex connected. If it is, the definition is very similar, but we should add here one thing. So if it has more than two, strictly more than two than K vertices, and then we have just the same, but for vertices, and for if we take not more than K minus 1 vertices, then remove it from the graph, and then the graph remains connected.
Yeah, okay, but in these definitions we see the difference between edges and vertices, because when we remove edges from a graph, then all the vertices are preserved, while if we remove a vertex, then we also remove all the edges that are incident to this vertex.
So we have the notion of vertex connectivity, which is denoted by mu of G. So the definition is just the same as this, but with H. Here one should write K vertex connected instead of KH connected. Well, for example, if we let's consider the graph, which is such a triangle with 3 vertices and 3 edges. So what can we say about these two invariants for this graph?
Ну тогда и вопросов не услышал, нет?
Нет, в смысле, уведомлений не...
Это я не знаю как.
F is 2, V is infinity.
Нет, слышим. What about infinity?
V. Or what is the second letter?
It's so this is edge connectivity, this is vertex connectivity.
Eta and this is a Greek letter, yeah?
No, I tried to write.
It's new or what?
It's new, yes.
It's new.
Okay.
Это...
Это is 2. New is infinity.
Well, I agree with eta, but I don't agree with nu. So this is, if we had not this, then it would be infinity, but we have but we know that the triangle is not three vertex connected since it has only three vertices. That's why it is only two. It's two vertex connected, but not three vertex connected, and that's why it is also two. Well, it indeed it makes sense because so we can say that this invariant, this vertex connectivity is also the least number of vertices that we can remove in order to make the graph not to be connected. And one may ask, when we're given a graph, one may ask, can we somehow remove several vertices in order not to make it connected? Well, if the graph is not...
If we remove two vertices, we have one vertex and it is still connected, right?
Yes. So when you have a triangle, we cannot remove any subset of vertices in such a way that the graph will lose connectivity. Whatever we do, it still will be connected. The same will hold if we have.
So it has maximal possible connectivity. You mean something?
Less than the size of the graph, right? Less than the number of vertices.
Yes.
Okay.
A kind of agreement.
Yeah, so this is the kind of agreement which works in case when our graph is full, and if it is not full, then everything is okay.
Complete.
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 It's complete. And if the graph is not complete, then we can remove several vertices such that it will lose connectivity, and the least number of these vertices is this vertex connectivity. Okay, so now let me state something about these two invariants. We have the following theorem. Firstly, we know that the second least eigenvalue of Laplacian is less or equal than the vertex connectivity, and it is less or equal than the edge connectivity. So then we have two estimates on edge connectivity, and they are the following. So let me first introduce some notation. Delta of G is the maximal degree in the graph. So this is the maximal degree of vertices of G. And also we'll denote by omega the number pi over n. So then we have
What's n?
yes, where n is the number of vertices in the graph. Then we have the following two estimates. So the last two results, they look quite complicated and weird, and indeed I I will not prove it completely. I will prove the modular some fact about stochastic matrices, and this fact I will leave without proof. And so I will show how can we.
My apologies. This indices of lambda are hard to see. What is the index in
Lambda
the
2. Lambda 2. This
So
is
this
always
is-
lambda 2.
So this
okay.
theorem is all about the second list, all about lambda. And so I will show how we can deal with this guy, but I won't show how this cosinus of omega appears. Yes. And what about the first statement? It is very interesting how to prove this part. And we will prove it completely. And this part can also be proved quite easily, but this is not about, so we have just inequality between two invariants, and this is not about Laplacian spectrum, it is just a corollary from some classical theorem from graph theory. And so now let us prove something.
Sorry, and who is delta of G, the max degree of what?
The
Well-
maximal degree of a vertex in a graph. Максимальная
Thanks.
вершина. Максимальная валентность вершины.
Okay, firstly, I'm going to prove this statement, but for this I will need some lemma. So assume we have some graph and assume that we remove several vertices from it. So G1 is G without some vertices U1, U2, UK. Then I claim that the second least eigenvalue of G1 plus K is greater or equal than the second eigenvalue of the initial graph. So when we remove vertices, the second lambda 2 can decrease, but it may decrease, but it does not decrease too much. Okay, so
But this can be proved if you prove that by removing a single vertex. Yeah,
yes, sure.
you decrease the second eigenvalue at most by 1.
Yes. So we assume that we remove just one vertex. So we want the second eigenvalue to decrease not more than by 1. And let us assume that our vertices are numerated by numbers from 1 to n, and we'll assume that we drop the last vertex. This is G minus.
May I ask a question? Is it clear that if you remove a vertex, then second eigenvalue decreases, or it's not true? Is it true or not true? Do you know?
I suppose it's not true, since, well, for example, if we start from the graph which is not connected, and we drop the whole connected, one of the connected components such that the remaining graph is connected, then lambda 2 was 0 and it becomes positive. So it's not sure.
Okay. And it is known that if for disconnected graph lambda 2 is 0.
Yes.
Yeah, because you have lambda 1 which is equal to 0. Therefore, for each connected component of a graph, adds a 0 to the spectrum.
And I probably missed. Why do we know that lambda 1 is 0 for disconnected graph?
Lambda 1 is 0 for arbitrary graph, because the sum of the elements in the Laplacian matrix is 0.
Right, yeah.
Okay, so we remove the nth vertex, and I will also need a graph which I'll denote by G prime. It is the graph which obtained from G by drawing all possible edges from the vertex UN. So in G there were some edges, but I add all possible edges from UN, and I call this G prime. Okay, and now I want to write something about the Laplacian matrices of these graphs. So I will need the Laplacian matrix of this graph G prime. What is it? It's look like this. It's a so here this is the square submatrix n minus 1 times n minus 1, and it is just the Laplacian matrix of G1 plus the identity matrix. Well, since if we remove UN, we have J1, and also all this H gives plus 1 to the degree of all these vertices. So we have plus the identity, plus the identity matrix. Well, what we have here we have n minus 1, since the degree of this vertex is n minus 1. And here and also here we have just minus 1.
Добавление ребер к одной вершине.
But here we don't think about the Vertex connectivity. It is just some statement about lambda 2. Okay. Now assume that we have so we have lambda 2 of graph J1. It is and suppose we have that V is the eigenvector with such an eigenvalue. So we have the following equality. Then let's see what will happen if I multiply this matrix Q of G prime by the following vector. So V is the vector of size n minus 1, and I want to write 0 from below and to consider this guy. And I claim that it is easy to see that it is the following thing. So in other words, this vector V0 is the eigenvector of the Laplacian matrix of
G prime?
of G prime with such an eigenvalue. Okay,
Yeah,
and that's why we can write the following inequality. Lambda 2 of G prime is less or equal than this guy. Because this is some strictly positive eigenvalue, and lambda 2 is the second least eigenvalue. That's why it is not greater. And also, I can write the following inequality. It is the lambda 2 of G prime is greater or equal than the lambda 2 of the initial graph. Why it is so? Because G prime is obtained from G by drawing some new edges. And we know that if we draw an edge, then any eigenvalue does not decrease. So moreover, we know that if we draw some edge, then the eigenvalues of the old graph and the new graph will interlace. So we have lambda 1 is less or equal than lambda 1 of the graph with new edge. It is less or equal than lambda 2, less or equal than lambda 2 with a graph with new edge, and etc. If we draw several edges, then the picture is not so beautiful, but nevertheless, we know that for any k, lambda k does not decrease when we draw edges. And that's why we have such an inequality. Okay, and it finishes the proof. So we have this is less or equal than this, and that's what we needed.
Right.
Okay, so we have lemma. Okay, now I'm going to prove that lambda 2 is less or equal than the vertex connectivity. Okay. So suppose we have some graph. We have the graph, and I will the set of its vertices will denote just by v, and suppose that v1 is some vertex cut. That means that v1 is such a subset of the set of vertices that if we remove all these vertices from the graph, it becomes it loses its connectivity. Yeah, surely I here assume that G is connected, since when G is not connected, this equality is obvious. We have both this and this equal to 0. Connected, and I consider some set of vertices such that if I remove them, G loses its connectivity. So we have something like.
Sorry, I missed previous seminar. And what is the goal of the whole lecture? I mean, this theorem, and after, what is our goal?
Well, my goal is to prove some nice results about some classical graph invariants, which connect this invariance with eigenvalues of Laplacian graph.
Of Laplacian matrix.
Oh, of Laplacian matrix,
yes.
Thanks.
So I have no some global goal, but I have some.
Yeah, I see. Yeah, thanks.
Yes, I will also assume that V1 is not the whole V. And we have at least two components here. Okay, now if I consider the graph G without V1, then its lambda 2 is equal to 0, since this graph is not connected. Then I'm going to use this lemma, and I can write that lambda 2 of G is less or equal than lambda 2 of G minus V1, which is 0, plus the number of vertices that we have removed, so plus this. And since this is 0, this is just this. Okay, then we know that for any vertex cut, its size is greater or equal than this guy. And by the very definition of the edge connectivity, it follows that this guy
vertex
is
connectivity.
Yes, vertex connectivity. Yes, so we have so for any subset of vertices, if we remove them and obtain non-connected graph, we have this inequality, and then it follows that lambda 2 is less or equal than the vertex connectivity. And just by the definition of vertex connectivity. Okay. So we have proved this. What about the second inequality? Let me also say a couple of words about it. So then the vertex connectivity is less or equal than the edge connectivity. It follows from such classical result as Manga's theorem. And Manga's theorem states the following thing, that if we have any two vertices in our graph, then there exist nu of G paths from the first vertex to the second vertex, such that these paths have no common vertices except the last vertex and the first vertex and the last vertex. So if we
for any pair of distinct vertices, there exist nu of G passes, yeah, and W1 and W2, and that do not have intermediate coinciding vertices. Yeah. Well. Может быть, нет, ну, конечно, для каких-то пар вершин там больше.
So if one can't throw out k vertices such that the graph loses connectivity, then any two vertices can be connected by k such paths. And this obviously proves this inequality. So when we remove, so assume that we remove less than this number of edges from the graph, then we can't lose connectivity. Why? Okay, let's just take any two vertices, and then there will be still a path between them, since we have k such paths, and they have no common vertices, and then they, since they have no common vertices, they also have no common edges, and that's why at least one of these paths will survive, and the graph is still connected.
Значит, если мы удалим из нашего графа некоторый набор вершин, количество вершин, в котором меньше, чем его реберная связность, то у нас между любыми двумя оставшимися вершинами все равно найдется, по крайней мере, один путь их соединяющий. Поэтому граф останется связанным. Да?
Yeah, so I'm not going to prove this. It's some classical result, and
Rather easy to prove, I believe. Not so complicated.
yes. Okay, so let me talk about these two inequalities, and so I'm going to prove that they follow from some fact about stochastic matrices. Okay, but right now we don't have any stochastic matrices, we just have our Laplacian matrix, and what I'm going to this is C. So now I'm talking about B and C. Okay, I'm going to consider such a matrix. I will denote it by S, and this is the following. So I take Laplacian matrix, I multiply it by scalar, which is the inverse of the maximal degree, and then I take it with minus and add the unity matrix. So what is S? So I can say that S is symmetric. All elements in S are non-negative. And also we have that rows and columns of S sum up, so they sum up to 1. Both rows and if rows, then also columns, since S is symmetric. What do you mean? Well, I'm not. Well, I don't think that it is. I'm not sure, but I don't want to consider such a representation, since this S is very much like Q. It is just some linear polynomial of Q. So it's not very far from Q, and it's not something completely new. But nevertheless, it will be a.
So you
we'll
mean
need
that
such properties of S.
You mean that this matrix is stochastic, yeah?
Yes. So, in other words, yes, is symmetric. Is symmetric stochastic matrix.
A matrix with non-negative entries is stochastic if each column and each row, a quadratic matrix, is stochastic if it's each column and each row sum up to 1. Yeah. Дважды стохастический. Double stochastic. Double stochastic matrix.
Okay. Okay, so in other words, we have that S is double stochastic. And so the fact that I'm going to use, but not going to prove, is the following, that if we have some double stochastic matrix, and we can define the following number. So we'll denote it by mu, and it will be the minimum over all. So let S be the matrix n by n, and let n capital will be just a set of integers from 1 to n. So columns and rows of S are labeled by this n capital. Then I will take a minimum over all non-empty and proper subsets of n of such guys. I will sum up all elements in this matrix over i's which are in this set and k's which are not in this set. For example, if this set is just several first integer numbers, then we will sum up all elements in such a rectangular. And so we consider all sums of this form and take the minimum.
Сейчас, значит, что тут происходит? Мы рассматриваем все... Какие подматрицы мы рассматриваем?
So I'm taking some subset of...
Мы берем некоторый набор строчек и дополнительный набор столбцов, да?
Yes.
Yeah. So we choose a submatrix formed by some set of rows and a complementary set of columns. And the complementary set of columns. This will be a submatrix, and for such a submatrix, we compute the sum of its elements, the sum of its entries, and take the minimum of all such sums. And denote this minimum by mu of S, yeah?
Yes. Mu of S.
Mm-hmm.
So then we have two inequalities on this mu, which look much like these two inequalities in the following. So yes, let me also denote by sigma 2 the second least eigenvalue. Of our double stochastic matrix. Okay, then we have the following two inequalities. Well, it's when we're looking at these two inequalities, they don't make much sense, and but nevertheless they are true, and I'm going to use them.
But what's omega for?
Omega is just the same as
for double stochastic matrix.
It is just the same as here. It is
Pi over
the size.
Pi over the size of the matrix. Yeah, I see.
Okay, but nevertheless, let us show how B and C follow from this fact. Okay, it is so we should connect somehow this this mu with H connectivity, and I claim that the connection is the following: mu is just the H connectivity divided by the maximal degree. And also I claim that the lambda 2 is also connected with sigma 2, namely sigma 2 equals to 1 minus lambda 2 divided by the maximal degree. Okay, this equality is almost clear from the definition, and it is easy to check. And also it is easy to check that from this fact. And if we substitute here sigma 2 as the following and mu as the following, then we will obtain this result. Okay, just some technical computation. And what we are, the most interesting part is this. So how exactly mu related to the H connectivity? And the relation is the following. So what is H connectivity? It is the least number such that we can, it is a least k such that we can remove k edges from the graph and such that it loses its connectivity. Well, what does it mean? It means that we can split all vertices of G into two subsets such that we have not more than k edges between different subsets. So this is the key point.
And this is essentially the same as being mu.
Yes, so if we split the set of vertices into two subsets, then the
edges connecting.
Yes, edges connecting vertices from different subsets are just written in this submatrix.
Okay, yeah, and I think the very remark that such a matrix is double stochastic is rather useful in studying graphs. Well,
I'm sorry, just a moment. Okay. So that's all about vertex and H connectivities. And one. So now let me. We have not very much time, but nevertheless, let me claim some results which relate eigenvalues of G with some other interesting graph invariants. So,
are there any useful statements about lambda 3 or lambda n?
There is something about lambda n. Now I will write it, but I don't know anything interesting about lambda 3 or any concrete lambda. So the lambda 2, it turns out that they display the role which is more important than the role of other lambdas.
Yeah, I see.
Okay, firstly, some result about lambda n and such invariant as independence number of the graph. I will denote it as alpha of g, and it is the size of the greatest size of the subset of vertices such that there are no edges inside this subset. And there is here will be two results. One result is weak and the second one is strong. First, actually, the first result is the following. Let us assume that G is deregular. So that means that all vertices of G have degree 2. And then the following is true.
In particular, D coincides with delta of G.
Okay, then alpha of G is less or equal than n times 1 minus d over lambda n. So such an estimate. And also we have a stronger result, which holds actually holds for arbitrary graph, so we don't assume anything about G, and A is false from B immediately. Okay, so now let us denote degrees of the vertices by d1, d2, and dn, such that they increase. And let us denote by ER the average of the first R degrees. And assume that the number R0 is such that the following inequality holds. So R0 is greater than n times lambda n minus ER over lambda n. Then I claim that the number of independency is less or equal than lambda than R0 minus 1. So we look at this inequality and we can consider such R0s that this inequality holds, and if we find the smallest R0 such that it holds, then we obtain such an estimate.
And why we cannot just take this number for R0? What does not allow us to take, just to set R0 equal to that number?
Sorry, this is here is also R0. So the right part also depends on R0.
I see. Now I see.
Yes, and in particular case, if we if our graph is irregular, then the right part indeed does not depend on R0, and yes, we just take the smallest R0 such that this holds, and we obtain this statement.
There is a graph invariant called the independence polynomial. Poly e.g. ig of say t, which looks like t to the power k ik, where ik k from 0 to maybe I don't know independence number of g. Ik is a number of subsets of k of independent subsets of k vertices. Subsets, independent k vertex subsets. Subsets. Whether there is some relationship between the roots of this polynomial and eigenvalues of the Laplacian matrix. Don't you know anything about that?
Well, in the article, this polynomial does not mention.
Mhm.
The
Okay.
question seems very interesting.
Okay, then. Mhm.
I can know that the first statement, in order to prove the first statement, one doesn't need Laplacian matrices, and it can be proved using so it was so this the first result was established by people which who studied adjacency matrix. Since this graph is deregular and that then adjacency matrix and Laplacian matrix, they differ just by some scalar matrix, and there's no big difference between their eigenvalues, so it can be formulated in terms of adjacency matrix, and so people who studied it, they established this result. But the second result is much more stronger. It is so it holds for arbitrary graph, and the second result can be proved in terms of adjacency matrix. So here we need Laplacians, and so here Laplacians they are more useful than adjacency matrix in this context. Well, now I will formulate a couple, some more curious results. So, firstly, let us consider the diameter of the graph. So, between any two vertices of the graph, we can define the distance between these two vertices. So, it is the length of the shortest path between them, and the maximum of distances through all pairs of vertices is the diameter. And we have the following estimate for the diameter. The diameter is greater or equal than the following guy, n times lambda 2 of g. So this is one more result on lambda 2.
Mm-hmm. The 4 in the numerator, yeah?
Yes.
Mm-hmm.
One more result is about the maximal cut.
Vertex cut.
No, not vertex cut, but
H cut.
about H cut, yes.
Mm-hmm.
So this is so this invariant is defined in the case when our graph can can have multiple vertices, and moreover, when our graph is a weighted graph.
Multiple edges.
Oh yes, multiple edges. So, but moreover, we can just assume that our graph is weighted. So just for any pair of edges, we have some weight of the edge between them. And we can consider some edge cuts, and the result is the following. So this is about the biggest eigenvalue, and the result is the following.
For the biggest eigenvalue, yeah?
Yes.
Do we have any estimates from above for the biggest eigenvalue?
Maybe well, I don't remember exactly, but maybe there are some estimates.
But don't mind.
Okay, so maybe there are some estimates in the article. So there are some numerous results that I did not stand here. So I just skip them and talked about most but most interesting of them. But there are many other curious results, and so I'm sure that there was also some interesting things there. Well, and one more thing that I want to mention, it is related to the applications of all the story, and I find this rather curious. So it is about some algorithms of graphs. Well, when we are, I can say something concrete, but if I consider some graph G and I want to do something with it, calculate some invariant or something, and I want to establish some quick algorithm for it. Then one of the ways that one can use is the following. So we can cut our graph into two parts, then use our algorithm for the first part and for the second part, and then somehow establish the general results from the results for the parts. So just some. It is very general logic for different algorithms. So we have some data. We cut the data into two subsets, then recursively run our algorithm on this subset, and then merge results somehow. And if you want to use this logic for graphs, one may want to one may want the number of edges between these two subsets to be small. Yes, indeed, we have some. We can consider some estimates by this number, but nevertheless, we want to establish some concrete cut, and one can. So of course, there are algorithms that find this cut, but they work for. They require
super
long time for work.
Super exponential.
No, not exponential, but it is polynomial of not very low degree. And one wants to find this cut very quickly, and there is some some heuristics that we may not to require this cut to be minimal, but it will be okay if this cut will be close to minimal. So there will be no, so the number of edges will be not too big, some close to the minimum one. And so how to find not the best, but the solution that will be approximate solution? Well, the way is the following. One can consider the let y be the eigenvector for lambda 2. So the eigenvector with value lambda 2. Well, and so we can consider vertices for which the component of this eigenvector is negative, and all other vertices for which this component is non-negative. And let us all these vertices go to the first part, and all these vertices go to the second part. And then this will be rather close to the optimum.
Nice. Thanks, Grigorii. Are there any questions? Misha, do you hear me?
Yes.
May I ask your comment about, it seems that I'm more or less sure that the Laplacian matrix of a graph should play a serious role in cluster algebras associated to graphs. But do you think that the eigenvalues, the Laplacian eigenvalues, can say something essential about the corresponding algebras, cluster algebras?
To be honest, I'm knowing about the Laplacian and cluster algebras, and I know nothing about eigenvalues and cluster algebras. It's a good question, but so to the best of my knowledge, no connection is still established.
I see, but whether Laplacian matrices appeared somewhere.
Мы находимся в масках. По-моему, я вам каждый день и целый день говорю. На факультете находимся в масках. Знаете, я вам дам маску, молодой человек. Знаете, берите, одевайте.
Sorry for interruption. Whether Laplacian matrices appeared explicitly in cluster algebras?
No, well, there is some connection between Laplacian matrices and this integrable system by Kenyan and Goncharov, because, well, this Castellane matrix is sort of square root of Laplacian. But it's more in the spirit of general connection between dimers and well, okay, I don't know. There is something about, there is some connection between dimers and Laplacian matrix, but I think it didn't play any role in cluster algebras.
Okay, but anyway, there is a direction in which we can think at least a little. Are there any more questions? If no, then I recall everybody about the summer school in Sochi in August, held by the International Laboratory of Cluster Geometry, and I suggest that everybody sign in.
Do we have seminar next week? No seminar next
No seminar next week. We have an
vacation.
all Russia
Traditional vacation.
traditional all Russia vacation
No. It's
for the first time this year. Yeah.
the High School of Economics is traditional.
For the High School of Economics is traditional. So we will meet in 2 weeks. Thanks to